Hello students, so continuing my lecture on graphene mechanics. We will start with the unit cell of a graphene. Now, whenever you are trying to find out the unit cell in a graphene, which is basically a two-dimensional sheet, you need to consider the translation requirements in only two directions. So, if we have a graphene sheet like this, in these two directions there should be a translation, and by translation we should get back the same structure. Then only we can consider that part to be a unit cell. So there are two ways by which we can define the unit cell in a graphene. The first one is the signal hexagon. So we considered any of the hexagons and we perform translation in either in x and y direction, we get the same hexagon back. So this can be considered as a unit cell. And the second one is is a combination of 9 hexagons, but actually not the full hexagons. So if we go a little bit, we draw the graphene sheet once again. And if we take so what more to do, add some few more. So if we take 3 of them, take 9 of these sheets, so we can form a unit cell. So these 9, this combination of these 9 hexagons taken partly or fully in some extent, we perform translation and rotation. Translation in these two directions, so we will get back the same structure. So this can again be considered as the unit cell. So this is basically a parallelogram consisting of parts of 9 hexagons. Now, what is the basic similarity between a hexagon and this parallelogram that we considered? Both of these have the same area. Means whether it is a hexagon or a parallelogram, both the unit cells have the same area. Now, when we are forming a nanotube, or a carbon nanotube in this case, then the translation requirement of a unit cell need to be satisfied only in one direction. So, translational requirement of unit cell only one direction, and that is of course along the length of the nanotube. So as we move along the surface of a nanotube, the pattern will repeat itself. So this nanotube can be considered and can be constructed by piecing together any one of these unit cells. So either we can have a hexagon or a parallelogram. We can have different pieces and we could construct a nanotube out of these. Now, second thing that is important in the case of nanotube mechanics is the two vectors called is the relationship between a translational vector and a chiral vector. So we have a translation vector C that we have already told you. It's NU1 plus MU2. Now when we are considering a unit cell, we are considering the translation. So the translation vector again can be represented in terms of these basis vectors u1 and u2. Only the coefficients will change. Instead of n and m, we will now have t1 u1 plus t2 u2. These are vectors. Now how do we find the relationship between them? Now what we need to do, we need to unroll a nanotube back into a graphene sheet. So we are doing the reverse case. Unroll a CNT back to graphene sheet. That means it's something like this. So this is your carbon nanotube, and this is the girth of it. You take a section, and this is where the translation is taking place. So if we could cut out this portion, it will be like a tin can, and if we again unroll it, it will be again take the shape of a graphene sheet. Let us say okay. Now here, as we have mentioned, this as the translation vector. So this remains as a translation vector like this, whereas this is your chiral vector. So C and T. Now C is always perpendicular to the T. Translation vector is always perpendicular to the chiral vector. So that is the case. The dot product C dot T will be equal to 0, and using this condition, what we ultimately get is we get the values of this T1 and this T2, and the value of T1 comes out to be equal to minus n plus 2m C, and the value of T2 is equal to 2n plus m plus C. So you can take this as an assignment, and you try to solve this relationship. And C, of course, is not this C, this is capital C, this is small c, this C is a constant. So let's put it as a key. I'll be confused, so put it as a key. Then this is some constant. Okay. Now, the length of this translation vector t is again found to be equal to root 3 L, and the area of this is your T and this is your C, the area in between T and C of the disk, cutout disk, that comes out to be L into T, because the modulus of C is L and modulus of C is T, so this is again equal to L into root 3L, so that becomes equal to root 3 L square. Now we have previously found the value of L, so using that value of L, if we put it in here, so the area comes out to be equal to 3 root 3 N square plus Nm plus M square divided. Okay, that's it. Now what about the number of atoms? How many atoms are there in this area? So that we can find. Initially we have told that all the unit cells are supposed to have a common area. That means whether it is a parallelogram or it is a hexagon, they are supposed to have the common area, and that is equal to AH. So we would like to find out how many carbon atoms are there. So what we will have to do now another reason of taking a hexagon is there are 6 carbon atoms, and each of its contributions is 1/6. So 6 into 1/6 becomes 1. So we would like to find out the number of atoms in this area of C and T. So that is equal to, we could divide it should become A into AH. That should be the number of atoms, but we add an extra 2 here. The reason of adding an extra 2 is that one carbon atom is actually shared by 2 atoms, 2 of the unit cells, so that makes it contribution 2, and so the value of this comes out to be equal to 4 into N square plus Nm plus M square. So this is the value. These are the number of atoms which are present in the area between T and L. Now there are 2 unique atoms inside each parallelogram bonds. Okay. So and every nanotube is geometrically equivalent to a nanotube where N and M parameters satisfy 0, M and N. Means every nanotube is geometrically equivalent to a nanotube where this condition is satisfied. This is the first thing, and the second thing is that the parallelogram, also I've already told you that the parallelogram and the hexagon, they both contain effectively two unique atoms beside them. So that is why 2a by a each, this factor 2 arises comes when we are finding out the number of atoms.